theorem on generalizing this theorem. Yeah, so please.
Okay. So yeah, today I'm going to talk about two complexes with unique embeddings in three spaces. This is a joint work with Agelos Georgakopoulos. So this Whitney theorem is a very famous one of the classic theorem. If you have a three connected graph G, which is planar, then if you have two embeddings on a plane or a sphere, then we can find the homeomorphism of the sphere such that the one is mapped to the other. So for example, I mean, if we have say K4, then we have 1, 2, 3, say 4. I mean, that is this way, and let's say even if you draw it on another way, then what you can do is that you map this triangle continuously to here, and you flip the outside and inside. On the sphere, outside and inside are same. Then this outside go to the inside, and you can continuously, I mean, mapping everything to here in a one-to-one way. And more generally, I mean, the complete characterization of the graphs with the unique embedding is known. So essentially, a connected graph has this unique embedding. In S2, if and only if is subdivision of these two things. I mean more than two things. So three connected planar simple graph. Or subdivision of these simple structure. So essentially all multi-graph with at most 3 edges. So they are the four graphs with this unique embedding. The unique means that if you have two embeddings, then you can find the homomorphism from the sphere to sphere. Here, considering the subdivision is quite natural, because I mean, in terms of this embedding, if you have passes with this vertex degree 2, and that and edge are both just curved, so they are same. So considering subdivision is very natural. And then why only this? I mean, 4 plus the 3 connected planar simple graph. I mean, maybe we can get some example to get some feeling. Okay. Yeah. Yeah. Anyway. Yeah. All right. So essentially, I mean, so we can try some simple example to get some feeling. So let's say, let's forget the loops. I mean, so this is kind of same with the subdivision of loops, right? Yeah. Yeah. So, and let's say you have just a star with 4 leaves. And if you have these two embedding, then they are actually different embedding. Because if you want to say, I mean, just imagine plane to plane, if you take a homomorphism, then these points have to be also some curves here. And also, is it visible on the YouTube that it started, right? Let's say this and this. And also there must be some, like a curve here, must be also be a curve here, but I mean, there is no way that one-to-one that we are mapping this plane to this plane. If we want to map this one-to-one, two-to-two, and so on. And similarly, if you have say this edge is 1, and this edge is 2, this edge is 3, and then there is something in here, and this is different from like 2, 1, 3, then you have some other structure here. So they kind of, give you a general idea on why, if it is not a subdivision of 3 connected, then why, these are the only one. So you can kind of analyze that if it is 2 connected or 1 connected, then you can kind of do like this kind of movement or like putting some things in a specific permutation to show that they have more than one embedding. So what we do is, this is our theorem. So let's say X is finite. Maybe I use several color. Simply connected. Some words that were not familiar with me before. I put some. Okay, not familiar with me still. I put some color where every link graph is 3 connected. So consider simply connected to complex where every link graph is 3 connected. I will explain what these colored words means in a minute. Maybe you already know for all of them, but maybe we can kind of go over what they are. So if you have every 2 locally flat embedding, phi and psi from this X to 3 space, 3-dimensional sphere, and there exists homeomorphism alpha, which maps beside alpha composition with pi. Okay, at least I didn't color homeomorphism, so it's not so bad that I knew what that means before. So, first, what are the 2 complexes? So it's like, you can consider like 3 uniform hypergraph, but instead of this like triple, you consider this triple as a disk, closed disk. And you actually a bit more generalized. It doesn't have to be triple. So this could be like this. Polygon like thing which are filled up. You can define it more rigorous way, but essentially you can consider like so take a graph, say x1, which is the skeleton of your complex, and say attach some closed disk along some cycle. So for example, simple case is that you take the K4 and every triangle you paste, take a closed disk and you face it, you put it and you glue it. then that's one sort of two complex. I mean, you can do it with, say, you can take a pyramid, and you glue a closed disk of a pentagon, and then closed disk of these triangles, and that's also two complex. So I didn't define it rigorously, but we kind of understand what it means now. And
So this was CW complex that you
yeah. So now, I mean, what are the simply connected? Simply connected means path connected from plus every loop contracted. So between any 2 points, you can connect them by passing through a curve lying on this X complex. And if you have any loop, then you can contract it. And this condition is actually necessary for the theorem. Because if you think about it, what you can do is you can consider a torus. Yeah? And then on the surface, you take some triangulated torus, but whose link graph is, I mean, I didn't define what link graph is, but whose link graph is not reconnected yet. So what you do is you fill up. So inside you put some more vertices and faces to actually, I mean, make it, it's like inside it's filled up, then you can actually make it satisfy this condition. But you can put it in this way, but also you can kind of put it, I mean, embed it in a knotted way. Yeah. You can put the exactly same the two complex in a knotted way in the space. Then they are not homomorphic. So if you don't assume simply connected, then the embedding cannot be unique. So that condition is necessary. And what does it mean by locally flat? Which color? So locally flat means that if you have your embedding and then you have these faces are embedded here, let's say, and when you embed this, I mean, this complex to space, and we don't allow two weird things happen, like some pathology doesn't happen. For example, what we mean is that on this space, which is closed disk, if you take a point here, and then if you take a small open ball around it, and then see how this open ball and the face are intersecting, then that should be roughly, I mean, that should be isomorphic to, I mean, R2 within R3. So it should be a ball which are cut by plane. It doesn't have to be plane, but topologically plane. And similarly, I mean, on the if the point is on this, I mean, edge, then if you take a small open ball there, then that should be look like a small open ball with several half spaces are kind of attached. Just like a normal way that you imagine. So no weird thing happens. And on vertex, also if you take some small open ball, and that must be something like a sphere with if you take the intersection, sphere with some sort of embedding of a finite graph here with I mean, origin here, and then each edge actually provides some faces which are flat way in here. So you can kind of imagine. So on a sphere, you draw some graph, and then you kind of shrink this graph continuously onto the center. Then that should, I mean, that should be the local structure here. So again, this assumption is necessary because if you don't assume it, And all sorts of weird things can happen. So one example is this Alexander Pond space. So you take, say, some sphere, just a sphere, and maybe you can consider it a triangulated sphere. It doesn't matter. I mean, topologically they are safe. I mean, here, how you put it is that, I mean, this is well-known pathological object. And then this kind of branches out in a way that maybe drawing this is almost impossible. Yeah, I failed. So generally, I mean, you have this like tube. This is sphere, and then you kind of divide it into two, and then you kind of cross it in a knotted way, and then you divide two again and cross in a knotted way, and you keep doing. So which is actually, I mean, homeomorphic to this sphere, but in a not locally flat way. So that we know that this is actually same as a sphere, I mean, homeomorphic, but its outside is not even simply connected. So this is one non-locally way of embedding this sphere, so that there is no homeomorphism of this space to this space, mapping this to this. But if you forget the entire space, then between this there exists a homomorphism. It doesn't just extend to the homomorphism of entire space to entire space. So anyway, this shows that this locally flat assumption is necessary. Yeah, maybe I should have defined what link graph means first. I mean, I didn't define link graph. So link graph is basically, I mean, I already used it. So if you have your complex embedded here, and for each point, you take a small open ball, I mean, small open sphere, say, and then see the intersection with this sphere. Now this face intersection with this sphere is just this curve. So it's on a sphere, there are some curves attached to it, which are graphs. So that's your link graph of this complex at this point. I mean, combinatorially, you can define like link graph Lx at B is just collection of UV, UW, the number of the edges, where you have V, U, W. For every such space, you add an edge between U and W. Then you get the collection of edges. And, I mean, that gives you a graph. That's a link graph. Simply because, I mean, no matter how you embed it in the space, when you take a small open ball here, and this space will give you edge between these two. And then you just identify this U with this edge UV, and W with edge VW, and you get the link graph. And what it says is that if the link graph is reconnected, then, and also if that entire X has embedding, locally, at least one locally cleared embedding, that should be unique. So, could you say again?
Will the link graph be defined if you have an embedding?
Yes, because if you take this, okay, if the entire thing is already embedded, you take this sphere, then it automatically gives you embedding on this surface of sphere, right? Yeah. And also, this finite condition is also necessary. I mean, I didn't color it because I mean, we know what finite means. But if you go, okay. I mean, simply for, say, graph case, you consider the grid, but you can draw a grid in a way that so this is y equal 1, y equal 1 over 2, y equal 1 over 3, and so on, y equal 1 over n. And you can draw grid in this way. And also you can draw in a normal way that x equal n, y equal n. If you consider infinite grid. And these two ways are different embedding because here you have some accumulation points, but here you don't. So this finite condition is also necessary. Technically, our proof also works if we, instead of finite, if we assume that the accumulation point free embedding. So you don't have accumulation, then it's also okay. And before defining one more term, let's define this. In this two complex, let Gx be the subgraph of the one skeleton consisting of edges belonging to at least three faces. So what it means is that if you have some edge which belong to only these two faces, this, and then there are no other edges containing this, then this can be actually same as just taking one big disk, right? There is not much, this edge is playing not much role, right? Topologically, I mean, this and this are same, unless I mean, there is another face using that. So just forget that on the graph, and that's what G of X. And then with this, we can actually prove a slightly stronger theorem than this. Our actual theorem is that, let's say, we define X is Whitney if every link graph RFP is a subdivision of three connected planar graph, or these two. So essentially, meaning that your graph is two connected planar graph with unique embedding. So here we know that all unique embedding ones are this. Out of this, you take the only two connected ones, and subdivision of three connected planar graph, and subdivision of these two, because other ones are not two connected. So instead of three connected, what we actually prove is that finite Whitney, and I just realized I didn't fully define it yet, and this G of X connected. Then we say this is Whitney, and if these two conditions satisfied, then that holds. Again, if you know that this G of, if you know that every link graph is three connected, then on link graph, every vertex has degree at least 3. That means that vertex is in your two complex, it's an edge. So that edge belongs to at least 3. So this is automatic if your, two complex is connected. Connected and link graph 3 connected. So this is actually a stronger one. So what we show is that, this holds. Again, if you think about it, I mean, these conditions are necessary. So these two connected, you cannot replace with one connected. Because if you simply quickly think about it, then you somehow put the sphere and then put the triangulation and then some additional things inside. And then let's say you have this one edge which does not have any faces inside. And here you just put this and like some other things here. Then these other things, so there is some space inside of this sphere. This other thing can be put outside or inside. You can just flip everything inside if their connection is just only one face. Then, there are more than one way. If the inside is not exactly isomorphic with the outside, you can put something to make sure that it is different. Then, if you think about it, this kind of structure is exactly link graph of this has a chord edge. So, it's necessary that your link graph is two connected. And similarly, this is also kind of necessary. With a similar example, you can also, cook up some example that the GX is not connected and it has a different embedding. So, how do we want to show such a statement that there exists, unique embedding? So, what we want to do is that you have some statement about the embedding, this information. Can we somehow capture this information in a discrete way? So that's something, we can ask. In fact, if we consider the graph case, there is something called rotation system, which captures the information about your planar embedding. So what is rotation system? Rotation system is in each vertex of your plane graph, or let's say just graph. On each graph, on graph, on each vertex, you consider a cyclic ordering. Of the edges incident with the vertex. And why do we consider this? Is that if you have some plane graph, you embedded it on the plane, and if you think about this, on this vertex, you have E1, E2, E3, E4, E5. Once it's embedded, you just stand on this vertex, and then you can, count these edges in a counterclockwise way. Then you get this cyclic ordering. So if you have some planar embedding, then it gives you one rotation system. And of course, if you have a somewhat different way of embedding it, let's say you embedded this in a different way, then you might get different rotation system. And of course, not all rotation system can be realized by this planar embedding. So we say that a rotation system is planar if it comes from planar embedding. So for the graph, we have this planar rotation system that give you some information about your embedding. If you know the rotation system, you at least know how these edges are put on the plane. And for too complex there is also such a concept, rotation system. Is now for each h, you consider say this h is actually it's not just an h but the directed h. So it could be xy and yx. We consider it differently. So cyclic ordering, where the of spaces containing E. So what you do is you have a HE and this space F1, F2, F3. And if you have an embedding, then you can get a rotation system. What you do is we consider this directed edge, right? So now you know that let's say in this direction we are looking at it, and then we count in the counterclockwise way. But of course, if you are on a different direction, you get the inverse of your cyclic ordering. And this actually induces the rotation system on its link graph. Because on this vertex, again, if you take a small ball, small sphere, and then consider the intersection, then each edge is become this vertex, and each base become edges. And around this edge, we know that how faces are located, and that gives you that around this vertex on this link graph, how this is, the edges are located. And we say that this rotation system on two complex X is planar if it induces a planar rotation system on each of its link. So this inducing is actually combinatorial property. I just explain it a way that you consider this sphere or something. But forget that. You just have a cyclic ordering, and then you know how the link graph is. Then from here, you can directly induce a rotation system. And if that's planar, then we say this is planar. Then, with this, it's a bit weird that here we just, this whole graph, you just define it. The rotation system is planar if and only if it comes from planar embedding. But here it is not. It's defined so that each link graph can be embedded in a planar way. Then you say that this is planar rotation system. And it is actually very non-trivial whether this actually rotation system captures the two complexes which are embeddable on sphere. And Car machine actually proved that if you have a simply connected simplicial complex, simplicial is not too important. It admits on embedding in R3 if and only if it admits a planar rotation system. So this direction is easy, just as I mentioned, you take this sphere, but this is highly non-trivial. And yeah, I haven't read the proof, but I heard that in this direction, he's using Perelman theorem, the Poincare conjecture. Yeah. Yeah, 2 points. In this case, all the faces are triangles. You can just imagine that. Yeah. But that's also not important. If you have, say, pentagon, you can just replace it with, you can kind of subdivide into this simplicial complex. And then for that, if you have a planar embedding, then original one has planar embedding. It's written in this way, but its simplicial part is not too important. Anyway, so what we want to do is that if we have x, then we have embedding pi, and then psi. It's embedded in some way anyway. It's difficult to do complex on a plane here. Yeah. Right. And what we know easily is that if you have say this Whitney simply connected, x with these two, then let's say rho is a planar rotation system. Induced by, maybe, let me write it in one go. Rho, this is rho, this was sigma, right? Sigma rho, okay. So let's say you get a planar rotation system. So we have embedding, and this gives you planar rotation system, this gives you planar rotation system. By this forward direction, easy direction. And what we can say is that then these two are same up to divergent. We don't know whether they are homeomorphic or not, but one thing we can easily show is that their planar rotation system must be either same or all reversed. Because what? Let's say here at B, you induce this rotation system of graph, link graph. And what we know is it's Whitney, so its link graph has a rotation system, which is same or reversed. So these are either same or reversed. And here again, these are also same or reversed. So only one thing we have to be careful is that what if they are same and they are reversed? If that happens, then it's different, right? But that doesn't happen if this belongs to at least 3 phases. This H belongs to at least 3 phases. Because from here, if they are same, so up to reversion they are same, so they are not reversed, they are exactly same. That means out of this directed HE, you know this F1, F2, F3, F1, F2, F3 have the same cyclic rotation. And from this point of view, it should be exactly the opposite. It should be exactly the opposite. So out of 2 choices, itself or reversion, we have to, this kind of determines which one this has. And that's why we have this condition of G of X being connected. So that this relation shows that these two, if they are same, they are same. They are reversed, they are reversed. And you can kind of propagate to all the vertices if that's connected. And now what we know that they have a same rotation system. Then now what we do is we define something called local surface. So what it means is that okay, maybe what we want to do is that on a graph case, you know that if you have a graph, then you have these spaces. Some spaces on here which are like partitioned by these edges. And on this embedding of this, then you have, once you embed it, also again, 3 spaces are disconnected, and then you can take the connected component, substrate basis. Let's say this is chamber. So you have chamber, 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 chamber. This is like faces. But what we know is that if we know rotation system, we know immediately what edges are in the boundary of the faces. Because what rotation system does is that the F1, F2, F3, I mean E1, E2, E3, E4 are in this cyclic orientation. Then you know which ones are consecutive. So that two are consecutive means that there is space which have both of them as a boundary. And then again on here, what's the next one to here? You can kind of, propagate. And then you can take the transitive closure, of this like a consecutive relation. Then they give you this boundary of the faces. So similarly on here, again, if you have H and face, and then they are adjacent, they are consecutive on the cyclic ordering, then there must be a chamber which has both of them as a boundary. Then this local surface is this boundary of chambers. And this is a purely combinatorial information. It just comes from the planar rotation system. We don't know how they are embedded, but we know that these faces together are boundary of one chamber. That's a equivalence relation. So you can take the one such class as a local surface. And what we know is now that each local surfaces are here some faces and here some faces. If we have a two, so this is graph. So, but it's difficult to draw too complex. So let's just say this is chamber. This is face and this face. Let's just consider graph case. And if we know that they are here and they are here, and if you know its inside is actually both disks, then these and these are homomorphic, and then you can extend this homomorphic inside to make these two parts homomorphic. So that's actually Schoenflies theorem, which is actually known. And for higher dimension, we can also do the same thing, generalized Schoenflies theorem. I don't know whether spelling is correct, but so if say is homomorphic to S2 and locally flat, there is automorphism of the 3 space mapping its equator to K. So basically, it says that in 2 dimension, whatever way you put this circle, loop, in whatever locally flat way you embed, you can, they are homomorphic, then you can extend this homomorphism to the inside of it. And similar, same way, whatever way you have 2 spheres, you put it in a locally flat way, you can extend your homomorphism inside. So if all local surfaces are here, and then if its inside is actually, it is actually sphere, and we are done. Because everything here is chamber, and then its boundary is already, homomorphic, same. We know that they are coming from the same set of, faces. And then if we can extend each homomorphism inside, in each chamber, then we just glue those homomorphisms together, then they give you a homomorphism between S3 and S3. So if all the chambers are actually sphere, the boundary of chamber are sphere, then we are done. But that might not be true. So, yeah. So there is some standard way to map it to equator. And then another thing, you can also map it to equator. Then that provides a homomorphism between these arbitrary locally flat embedding.
I was curious about this situation in a graph. You might have a phase which is not a super cycle,
Right. That's actually the reason why we are not done yet. Yeah. So in graph case, we can have, say, for example, this is space, right? There could be some other thing. Same way in the, looks same. So what I wanted to do was take the sphere and then you just glue two vertices. Yeah. You see. Yeah, okay, looks same. Anyway, so this could happen, right? Then, you cannot use this. You don't know. This is not even surface. At this point, this is locally not, isomorphic to Euclidean space. So anyway, what we do is we consider something called flattening. What you do is you have this, say, graph G and complex X. Let me again explain in graph way. What you do is you have this vertices. And you put a duplicate of these vertices. Then put additional edges to take this supergraph. Then, in this way, so we put additional vertices. Then in here, what we know is now all the faces are actually just a disk. You can do similarly for these two complex as well. But what's good about this is that this can be purely defined combinatorial way. And also, once these two are already embedded, this is X, this is psi X. That's combinatorially defined, but defined in a way that it's compatible with this embedding, so that we don't know how these local surfaces are put in, and then we don't know what's inside. But there, you can actually put these vertices in that space. Then, while this is not changed at all, you can actually find whatever this fattening is. You can actually extend this to embedding of this fattening in here, and embedding of this fattening in here. Where once we have this embedding, and if you just restrict to X, then we have exactly pi. So you have this embedding here. And then now here, what we can check is that this fattening is also Whitney. And then they get a planar rotation system. And then they have to be again same on these two. And then they give you local surfaces on this fattening. And those local surfaces are now actually just a ball. Local surfaces is sphere, and then inside is ball. And you apply this generalized Schoenflies theorem to get a homomorphism between these two. And then you restrict your homomorphism to X, and you can get a homomorphism between spaces which maps the pi to psi. So that's the proof idea. And yeah, it's about time. So one obvious question is that we have done it in 3 space. So what about n space? N space, you can kind of again define its link graph being planar, and link graph being planar link graph has unique embedding, which is defined on its link graph to be unique embedding, and which is defined on its link graph to be also unique embedding. Anyway, you can do that. And it seems that many of the places that we did can be done with a higher dimension. But there are certain places that we don't know how to do it. So one of them is that when we actually show this local surface is actually like manifold, or like the surface after doing this fattening. What we do is there is this one point that at each vertex, if you just take the faces around this, then it's locally just disk. And that part seems, I mean, we don't know how to generalize into the higher, I mean, cases. So at some vertex, if you take a certain, on this boundary of local surfaces, if you take the bases around it, can we show that this is just a locally, and I mean, high dimensional disk? Yeah, so anyway, so I will finish here. Thank you for listening.
Thank you. Any questions?
Can you extend the feature just for two connected ones, not necessarily having a unique embedding, so that if we choose 3 or more embeddings, then there are at least 2 of them, they are connected via homomorphism?
Wait, I'm not sure if I understand you correctly.
Condition that they should have unique embedding, then can you show that if we take more than 2 embeddings, there are still at least 2 of them which can be connected via homomorphism?
So you mean there is
Actually, two, instead of unique, there is actually 2 different embedding? I don't know. Right, I am not sure if I understand your question correctly. Sorry, but I'm not sure whether that's a right way to generalize or I don't know.
operations that can characterize like distinct embeddings, like Whitney and things like that?
I don't know. Oh no, I mean, so we don't. No, I mean we don't have any operation for that. But I mean, for different embedding, you can, if this is Whitney, you can just check the rotation system to see whether they are same embedding or not. I mean, no, for Whitney it's unique. So for not Whitney one, if they have the same rotation system, then they have to be homomorphic embedding, I think. I mean, so one part is that we use Whitney to show the polynomial rotation system are same. But if you are already given that, then after that you just do the fattening and then make the homomorphism and then just reduce it. Then, yeah, same. I mean, you can just check the rotation system to check whether they are same embedding.
So, did you completely characterize does Whitney completely characterize the cases where there is a unique rotation system?
No. So, for example, you just take the sphere, right? You obviously it has unique, but your GX is just isolated vertices, right? Yeah. I mean, maybe. I mean, so those cases that the case that I just said is kind of stupid case.
Yeah, that's what
So maybe I don't know. I mean, I didn't see any simple way to characterize it. It is kind of like essential. I would say essentially characterized, but I don't know. I mean, our theorem kind of essentially characterized.
You seem to get one direction very well, right? Like if you satisfy this, then you get the unique embeddings. But what do you get in the other direction? Like if you know that there's unique embedding, what can you say?
Yeah, I'm not quite sure. Yeah, I'm not quite sure.
You should get something like if you have a unique embedding, then the rotation systems are the same after this reversion thing. This you should probably get it after Whitney, right?
Yeah.
But maybe you could have like some of the, because you sort of, it seems you sort of go this way that you, all of the
all of the link graphs have these unique rotation systems, and then that forces the structure of the rotation system globally. But maybe you could have maybe the global structure could force the local structure, right? Possibly.
Right, but it could be that all other vertices link
graph has unique embedding, but there is this one vertex link graph could have two, but the one is compatible with the other one may not.
Yeah.
I don't know.
So for the generalization for the possible generalization to higher dimensional complexes, do you have an analog for these planar rotation systems, or?
I mean, you can define it in a similar way.
Yeah, but you're missing like an analog of Johannes's theorem. Probably.
Right. That's
Also not, but one direction, we actually don't use the difficult direction. Oh, where is it? We only use the easier direction. That easier direction must be true, right? If you have embedding, then the system should be planar. But the other direction, we don't actually use it. So difficult.
So in a sense, like you could, I mean, to me it sounds like uniqueness of embedding could be a lemma to prove Johannes's theorem, right? Because you can use that to say that something is not embeddable. I'm not sure. I don't know, maybe you can use this.
I mean, well, my guess would be that what you get is if you don't have like two distinct.
If you call the proof of Minkowski's theorem, you use the fact that the three connected graphs is unique embedding, and that's how you prove that some graph is like non-planar, right? So maybe this could be used as a lemma to prove something useful for higher dimensions.
I don't know.
Yeah.
For the graph case, I mean, Whitney theorem, is there any generalization? I mean, can you select rather than the sphere? Can you select any other two surfaces, like toward?
I don't know. Yeah, I don't know. Yeah.
If the condition simply connected is necessary to guarantee that the complex has a unique embedding.
Yeah.
I mean, if there a complex that is not simply connected but has a unique embedding in S3.
Not simply connected.
Possibly have a unique embedding in S3.
I feel like. Wait. Okay, so stupid one is cycle. That's a cycle. But
You can't do much wrong with that.
I mean, so shift day. Ah, right. Yeah, you can try or not. Sorry. Yeah. Right. So. Right. I feel like if you're not simply connected, then not unique. Okay.
You may not be a but you do.